Okay, back to the problem that we left off with, where I'm asking a whole lot of questions about this system of two blocks sliding on a frictionless flat plane that's connected by strings. And we already found the acceleration of this whole system. It accelerates as a unit to the right at 1.67 meters per second. And we also discussed that string 1 has to have a greater tension in it than string 2, because string 2 is only dragging 2 kilograms behind it, whereas string 1 is dragging 3 kilograms behind it, and they're both accelerating those at the same rate. Bigger mass, same acceleration means you need a bigger force. That's F net equals ma. Okay, question C, I essentially answered this before the video ended, but what is the tension in string 1? Notice that if I'm pulling on string 1 with 5 newtons, the string 1 is pulling on me with 5 newtons, and by definition, the tension in the string is however hard it's pulling on something at the end. So if it's pulling on me with 5 newtons, the tension in string 1 is 5 newtons. That's pretty easy once you get the idea of it. D, what is the x component of the string force that, what is the x component of the force that string 1 applies to box A? And again, that's an easy one to answer, because if this has a 5 Newton tension in it, it's pulling on box A with a 5 Newton force. So the x component of, I put it sort of a complicated, often I'll do this, put a complicated subscript on it to remind me what a symbol means. This is the force of string 1 on box A, x component. And it's 5 newtons, right? String 1 is pulling to the right, and that a force that's directed to the right is in the plus x direction, so it's a positive 5 Newton force. So far, so easy. All right, now we have to think a little bit more to figure out the tension in string 2. We have a choice here. We can't just use the 3 kilogram object as the subject of a free body diagram in order to figure out the tension in string 2, because it's not a force reaching in from the outside and pulling on that. So what we need to do is limit our free body diagram to either the 2 kilogram or the 1 kilogram mass. It seems like the 2 kilogram one is a little bit simpler. We'll find out if that's what I did here. So let's do a free body diagram for the 2 kilogram mass. Oh, I'm sorry. I can't remember why I put that slide in there. What's the tension in string 2? Well, the tension in string 2 is the same as the force with which it's pulling on the sides. So if I'm treating the 2 kilogram object as my subject of the free body diagram, then the tension in string 2 is going to be one of the forces acting on it, and I might be able to solve for it. So here's the free body diagram for the 2 kilogram mass. Of course it's got a weight force. Of course it's got a normal force, and there's no friction force because we're on a frictionless plane. If we're only concerned here, again, with x components, because I want to solve for that T2. Essentially, the answer to this problem is T2. And that's only along the x direction, so we're going to do F net x equals max, or the sum of the force x components equals max. And there's only one force with a non-zero x component. This force has 0 x component. It doesn't point at all along x. This one also doesn't point at all along x, or going from tail to tip, you don't have to move along x. T2 has a positive x component because it's directed along plus x, or more or less along plus x, in this case exactly. And so it comes in with a plus sign here. So I get plus T2 is equal to the mass of the object in the free body diagram. In this case, that's 2 kilograms. That's one of the reasons I always write it in my free body diagram, so I can just read it off there, times its acceleration. We already found out that the acceleration of A or B, or the whole of A plus B, there's only one acceleration associated with all of them. It was about 1.67 meters per second squared. So that's telling me how to solve for T2. I just multiply those together, excuse me, and get 3.33 newtons. F, what's the x component of the force string 2 applies to box B? Well, that sounds like just a rephrasing of the same thing, right? If I know the tension is 3.33 newtons, string 2 is pulling on block B to the right. That's a positive force x component, right? because it's in the same direction as the plus x axis, and therefore the x component of the force of string 2 on blocks B is 3.33 newtons. We already knew that. G, what is the x component of the force string 2 applies to box A? Well, string 2 on box A is pulling to the left. So that x component of that force is going to be negative, right? It's pulling to the left, but plus x is to the right. Other than that, the magnitude of the force is 3.33 newtons. Again, it's the tension in the string, which is how hard it pulls on either side. So the answer in this case is minus 3.33 newtons. A lot of these, a lot of times in these worksheet questions, or even on exams, sometimes I'll ask things that are very easy to answer. They're checking to see if you know how to just read the language. Even though you've already found something out, you might just have to put a minus sign in front of it, and you already know the answer, if you know how to think about it. So this was one of those kinds of problems. Now, second thing we want to discuss, we just discussed properties of strings. Here are two objects, a 1 kilogram mass and a 1.2 kilogram mass, which are connected by a string which is looped over a pulley. Right? Pulley is like a wheel that can spin, and this particular pulley is a one we're going to use a lot in Physics 110. It's sort of an idealized pulley. It's a massless, frictionless pulley. Massless means, hey, don't think of this as a big heavy iron barbell plate. No, it's something that has almost zero mass, so it can rotate very easily. And furthermore, there's not a lot of scraping right here at the rotation point of the pulley. Rather, it's very well oiled, so there's not a lot of scraping that happens at all. So we're going to ignore the friction from the rotation at the axis of rotation, or the axle there, and we're also going to ignore any mass of this. And so we need to discuss some properties of massless, frictionless pulleys. So in Physics 110, at least for right now, we're going to assume the pulley wheel is massless and spins without friction, and that was said explicitly in this problem. I say for now because we are going to treat later on things that are like heavy barbells and be able to solve problems with them. But for right now, we're going to assume this has no mass and spins without any friction. And if that assumption is true, if it's massless and frictionless, then we're going to find that the string tension has to be equal in the strings on the two sides. Normally we might have supposed that there might be a different tension on this side than this side, but the idea is if this thing is massless and frictionless, it has absolutely no hesitation to starting to rotate. And if these two tensions were ever different, this pulley here would immediately start rotating to balance out the tensions. In other words, if the tension were greater on one side than the other, it would cause it to start rotating, and that would, because there's no hesitation to rotation for a massless, frictionless pulley, it immediately balances them out. So the idea is when we say massless and frictionless pulley, we can immediately assume that on both sides the tension is the same. That's good, at least for right now in Physics 110. If we talk about a massive pulley here, then all bets are off. For example, if I had a really massive iron barbell and I pulled down on this cable, or this piece of string on the bottom, and on this side I had hanging a little piece of styrofoam, you kind of had the intuition that there would be, because of the styrofoam's on, there would be hardly any tension over here. But if this thing were really massive and I had to pull really hard to get it to start moving, I might have a huge tension over here and almost no tension on this side. That's because that's a massive pulley. But here we're going to assume that they balance out because the mass is negligible. Okay, so how are we going to start solving this problem? Well, this again is a step up in complication from the one we just did. We had things connected by strings, but at least they were moving in the same direction, right? Both those boxes were moving to the right. Here, one box is going to fall downward if we let this thing go, and the other one's going to go upward, so they're not even moving in the same direction anymore. And so we have to kind of divide and conquer here. We can't really treat them as a unit, or at least we're not going to. There is a way to think about that, but we're going to try to not do it that way because it seems superficially more complicated. So what I'm going to do is draw a little diagram of the system that looks like this, and I'm going to try to First of all, I'm going to draw a separate free body diagram for this object and for this object. And I'm going to attach coordinate axes next to them, which I call consistent coordinate axes, which means that if this block is moving in the positive coordinate direction, then this block should be moving in its positive coordinate direction when the string is, pulling it as it normally would. So that means if I choose plus y to be up for this one, and I'm free to choose it down, but I kind of figured here, at least in this case, I know the 1.2 is going to fall and the 1 is going to rise if I let them go for rest. So why not choose plus y to be up there? If I call plus y up for this one, when this one goes up, this one's going to go down. So I better call plus y down for this one. That's what I call a consistent coordinate system for these objects. If you don't choose that, you almost for sure will make a sign error when you're doing the algebra for this, and I'll try to point out where that comes later on. Okay, let's do the free body diagram for the 1 kilogram block. I put a 1 on this little block-shaped object here to remind me that it's the 1 kilogram one. The positive axis direction is up. I don't know what the tension is in the string, but I'm just going to call it T. And again, we're going to assume that it's the same tension T on both sides. So on this 1 kilogram block, T is pulling up and its weight is going down. Its weight is 1 kilogram times 9.8. So that's its free body diagram. For the 1.2 kilogram, well, I guess I'm writing down F net equals MA for it first. So let's write down, if I call this, the X direction or the Y direction here, if we do F net Y equals MA Y, the T comes in with a plus sign because it's pointing in the plus direction, and the 1 times 9.8 comes in with a minus sign because it's a negative Y component for our chosen plus Y direction is up. So that's sum of the force y components equals the mass of the object in the free body diagram, that's 1 here, times the unknown ay. Now, we're asked here, with what magnitude does the system accelerate? I want to know what ay is, but unfortunately I don't know what t is, so I can't solve for ay yet. If I only knew t, I could solve for ay, but we're not done yet. That's not surprising because we haven't used any information about this other one. So let's go ahead and draw its free body diagram. The 1.2 kilogram object has the same tension T pulling up on it because it's connected by a massless, frictionless pulley going around there. And its weight is 1.2 times 9.8, and that's going down. But we have to remember to choose the consistent axis direction here going down. And so when I write F net equals MA Y components, where Y is going down for this one, I get the 1.2 times 9.8 here comes in with a plus sign, and the T comes in with a minus sign. This is the mass of the object in the free body diagram, that's the 1.2 kilograms, times the unknown AY. And here's where the consistent axis direction is really important. Notice that I use the same symbol for AY here. In other words, when this thing is moving with a certain velocity, this one will be going down with the same velocity, and so they're both accelerating with the same acceleration magnitude. But if I chose both axes directions to go up, when this one's acceleration is positive, this one would be negative, and so I wouldn't be justified in using the same symbol for them because would AY be positive or negative? It can only have one value. Whereas in this case, when this one accelerates upward with a certain AY, this one accelerates downward with the same AY, and they're both positive, and so I'm justified in using the same symbol for them. So that AY really means the same thing. That's the AY I want to solve for. Okay, how do I proceed and start solving for AY? I don't know T, and I don't want to know T. So I've got a system, what we would call a system of 2 equations and 2 unknowns. I've kind of put half a box around each one of them. And the way we solve that, back from your high school algebra days, is we do what's called substitution. We solve for the variable we don't want to know and substitute into the other equation. So I'm going to take this second equation right here, solve it for t. Okay, I just have to add 1 times 9.8 to both sides. So I get t is ay plus 1 times 9.8. And I'm going to take that expression for t and substitute it in up here. So what I want you to do is try to substitute that in for t up there and continue solving for ay And once you found AY, well, of course, I threw in a little kinematics problem. Once you know the constant acceleration of these two objects, you can figure out how long in time it takes the 1.2 kilogram block to fall 0.8 meters. So try to add on that little kinematics problem, and we'll be back with the solution.